Good afternoon, everyone. I'm Sara Vitali, and I'm from a PhD student from the University of Diego Portales. And thank you for letting me present this work today. And this project started with my master thesis at the University of Potsdam, and kept going during my first semester of the PhD. The project is about the study of the Sagittarius dwarf galaxy, and especially focusing on its metallicity analysis. So already in the first presentation, you heard talked about Sagittarius, which is a very interesting dwarf galaxy that is currently ongoing, is an ongoing merger with the Milky Way. So Sagittarius was discovered in '94, and it is composed by a core, which is the leftover of the old progenitor of the system, and also presents two wide stellar streams that wrap around the Milky Way that are the results of the tidal disruption that is caused by the tidal interaction with the Milky Way. So Sagittarius, as I said, it's a very unique laboratory to study the interaction between a dwarf and our galaxy, and it also presents a very complex and rich star formation history that brought to the formation of different stellar populations. So we know that Sagittarius is mostly dominated by an intermediate age population, quite metal-rich, but it's also known to host a very old and metal-poor component. So we were interested to examine the different stellar population using photometry from the Pristine survey. And the current work is now on a paper that appears in the archive. So, as I said, we studied the metallicity of this system using the data from the Pristine survey. Pristine is a narrowband survey that used a narrowband filter centered on the calcium H&K lines, and you can see the asynthetic spectra calcium with the two lines at in the bottom panel. So Pristine also used combine this metallicity-sensitive photometry with broadband photometry, with SDSS, but later on also with Gaia broadband photometry. And you can see the example of color space of Pristine in the bottom panel, where you have a combination of the calcium H&K term with the E and G photometry from SDSS. And as you can see, this color spread, this color space allows to have a clear spread in metallicities with uncertainties only of 0.2%. So what Pristine does is to use photometry to study and search for the most metal-poor stars in and around the galaxy. But now let's come to how Pristine has combined the data also from Gaia. And this has been done in a sub-survey that is called Pristine Inner Galaxy Surveys, that specifically focuses in the inner galaxy. So PIX looks through the galactic bulge to gather and analyze the metal poor star present in the bulge. But this sub-survey had reached quite low declination, and therefore it had covered also part of the Sagittarius region. And you can see the fields of peaks in the orange squares that appear in the plot, and the red circles are the one where the Sagittarius fields have been observed. And for these fields, peaks had also gathered some spectra with a follow-up. So measuring and getting low and medium resolution spectra. So what I've been doing is to combine the photometric sample from peaks with the Gaia GBP and RB photometry, and to study the Sagittarius system. So we used Gaia astrometry from EDR3, first of all to isolate Sagittarius member, because Sagittarius, lying on the opposite side of the galaxy from respect to the sun, it is in a very tricky region, because we have all the contamination from the Milky Way when we look at the system. Therefore, it was very important for us to have the cleanest selection as possible while building our sample of Sagittarius system. So for this, we used proper motion and parallaxes. And for example, you can see the proper motion space where the Sagittarius over density is surrounded by the red circle. And these are Gaia proper motion subtracted for the mean proper motion of Sagittarius. And we then applied also further cuts, and we cross-match and always try to anchor our results using spectroscopic data. And this is also where it's very important to have a synergy between different surveys. So we use the follow-up from the peaks itself, plus metallicity from the APOGEE DR17. So as I said, we first of all applied cuts in using astrometry. We also set a threshold in magnitude, so we limit our sample to 70.3 in the G band, and this was done to avoid the red clump and horizontal branch region, where metallicities were were harder to be inferred, and also where the pristine photometry is not well constrained. And we applied then further cuts in on quality and variability, and we arrived to define basically 45,000 members for the Sagittarius system. And you can see them plot for them the color magnitude diagram and the color diagram on the right, whereas again there's the pristine calcium H&K term appearing on the y-axis, and the two dashed line illustrates. The red one is a further cut that we applied for get rid of this cluster region around 0.6 in BPRP that was found to be still a contamination from the Milky Way, while between the two dashed line you can see another sequence that also appear in the color magnitude diagram around here that we discovered to be red clump helium burning stars. You can see the same color magnitude diagram, but with overplotted spectroscopic metallicity that we had at disposal for Sagittarius. And we also checked the goodness of our selection, plotting the radial velocities from APOGEE and peaks. So the peak sample is the blue, while APOGEE is gray. And also we looked at the metallicity range that we covered with cross-match with these two spectroscopic surveys, and you can the dataset, and you can see that combining APOGEE and peaks, we had a quite good coverage on a wide metallicity range. So we also, for perform our metallicity analysis, we used a halo calibration sample that was built for the main pristine survey, so that was basically built for the halo stars, and that was carefully built to contain very metal poor stars, but to which also we add APOGEE metallicities, and from which we just selected giant stars, because our Sagittarius sample is composed by giants. And you can see the color space where all the spectroscopic metallicity plotted. And as you can see from the plot, there is a quite nice spread, a vertical spread that basically allowed us to fit some polynomials in step of 0.5 metallicity, and therefore dividing Sagittarius in different metallicity groups. However, this spectroscopic sample was calibrated on halo stars, and the halo sample and the Sagittarius have different calibration on the calcium H&K terms. Therefore, we needed to shift along the y-axis the values in order to be on the same scales of the PIX photometry. And we did that thanks to the spectroscopy available. So therefore, we constrained our metallicity group, shifting them to match the spectroscopy in the same metallicity range. And we try to isolate different metallicity group. For example, we looked specifically at stars below -2 or -1.5 and -1. And as you can see on the right part of the dashed line, the halo training sample shows some problem because the sequences of metal poor and metal rich stars tend to cross each other, and this is a hypothesis that is due to a dependence on the alpha abundances, so a degeneracy between metallicity and alpha abundances. But if we look for our Sagittarius sample, we can see that here, thanks to metallicity from APOGEE, we are quite sure that these redder stars or cooler stars are can be classified as with metallicity above -1. So we took this different metallicity group or stellar population, and we plot them in space, so using our APOGEE from Gaia. And we built this density map to have an insight about the different distribution versus metallicities. The first column specifically illustrates the metal poor samples. The column in the middle represents the metal poor counterparts and the metal rich counterparts. And what is very interesting is was plotting the ratio between the metal poor and metal rich population in space along the Sagittarius footprint. And even if we are choosing different metallicity cuts, we can appreciate the same trend, and that seems that the relative number of metal poor objects tend to grow, moving at the edges of the galaxies, and decrease while staying at the very centers. We then focus this analysis just selecting our metal poor and metal rich stellar population, and we decide to set as metal poor stars with metallicity below -1.3 and as metal rich stars with metallicity above -1. We let this gap between the two definitions to be sure to not have a contamination from the two metallicity groups, so that stars metal poor jump in the class of metal rich stars. And again, we plot the ratio along the Sagittarius footprint, and this was confirmed the previous plots. That therefore, we tend to have a concentration of metal poor stars at the edges and also at the onset of the Sagittarius stellar tails. Also, we choose a metallicity at -1.3 because this is the estimated alpha Ni for Sagittarius, and therefore this value, or looking at stellar population below and above this value, could give us information about the star formation rates for different populations. To have a further insight, we fit some model to the stellar distribution of these two populations, assuming a exponential distribution and an elliptical distances. And we then have here the models for our Sagittarius stars. You can see the metal rich population at the bottom panel, and the metal rich the metal poor at the top panel. And on the right, you can see the residual between the models and the data. And then we had a look at the different structural parameters that describe this distribution to see how how the two populations show differences. And so the difference between the parameter, we have the centroids, the central density, the scale radius, the ellipticity, and the position angle. Apart from the central density that varies a lot between the two populations, but this reflects the outnumber of metal-rich stars compared to the metal poor, we see no very significant difference. We can appreciate a shift in the RA component of the center of the two distribution, and we have the metal poor stars that shows an off center this center, because this can be due to the fact that metal-rich star formation burst occurred more in the center respect to the metal poor one. And also what was interesting to notice was a difference in the scale radius parameter, that this difference is in line with our previous findings, meaning that the metal poor population that presents a greater value of the scale radius is telling us that the stars part of the metal poor population are more smoothly distributed and homogeneously spread along the footprint, while the smaller value of the scale radius for the metal-rich population is telling us that this category of stars is more centrally concentrated or segregated at the center of the galaxy. We had a look at the very metal poor population of Sagittarius, and we applied a selection using a polynomial or a isometallicity lines at -2, and we select more than 1,000 photometric candidates that, however, presents 100 stars in common with the spectroscopic peaks dataset. We then also looked at the spatial distribution of this population to have an insight of how the older components of Sagittarius are now hosted in the galaxy. We found them to be quite homogeneously mixed along the galaxy. Even we can see a higher density around the nuclear cluster that Sagittarius hosts, M54, and we can see here cluster of stars that correspond to the known cluster Tarzan 8. And this homogeneous distribution of this old population is telling us that these stars were not recently formed in the center of Sagittarius, but actually they had probably the time due to the tidal interaction with the Milky Way to be spread and push them towards the stellar streams. And yes, this also, even if all these candidates have not a cross match with spectroscopy, this is one of the largest very metal poor selection for the Sagittarius system. We then decided to spot a possible metallicity gradient within the core of the system, and to this purpose we divide the galaxy into concentric rings, and starting from the center that is given by the models that I showed you before, for which we took the metal-rich part. And we then compute the ratio between metal poor and metal-rich stars for each rings, so to have information on the variation of this ratio moving along the semi-major axis of the galaxy. And apart from the first rings, where it's clear that there is a contribution from the metal poor nuclear cluster, we can see a clear trend that hints that the relative number, again, of metal poor stars grows moving far from the centers. And this basically, it's kind of the same results that I showed you before with the density map, but that now we performed for all the footprint. So covering basically an area of 12 degree or almost 6 kiloparsec moving far from the center. However, we are aware that our analysis could still have a sort of uncertainties. For example, we are not covering all the magnitude that we have disposal from Gaia, but we are just taking the 80% of the original sample. Even if we tried our best to get rid of all the Milky Way stars, we could still have some contamination from Milky Way stars. For example, we took some, but to be sure that this contamination is not affecting our results, we test and we took 3 control fields from Milky Way stars, and we plot their distribution, and we see that they are concentrated towards the galactic plane and less concentrating in the region where we have our metal poor stars. So meaning that our metal poor sample should be quite clean from Milky Way stars. And also we plot possible contaminants in the color space, and we find them to be basically present in the red clump sequence that I showed you at the beginning, but however, they are present at all metallicities, so quite spread along the y-axis. So this should not affect our metallicity analysis. As I showed you before, we have a problem with the isometallicity lines, meaning that the halo training sample is not working very perfectly for cool stars, where where this part presents a degeneracy between metallicity and alpha abundances. And we also tested that our the metallicity gradient that we saw does not depend on which metallicity group we take. So we test our results on different class of different stellar populations. And finally, we the model fitting that we performed is kind of a simplification of the real distribution of Sagittarius stars. That therefore we have to be careful in interpreting the parameters and the difference between metal poor and metal rich population. But however, we could conclude that the metallicity analysis that we performed, thanks to the combination of Pristine and Gaia data, enable us to have an homogeneous investigation along a very wide area of the Sagittarius region, and to divide our sample in different stellar population. We were able to spot a trace of a metallicity gradient that is extended along the entire Sagittarius core, and that is telling us that Sagittarius has a more metal-rich population concentrated at the very center, while the metal-poor counterpart is more diffused, and the ratio is increasing at the edge of the galaxy. We fitted models finding different values for the scale radius, so hinting on different distribution for the two populations, and all these finding together suggested us to hypothesize that Sagittarius could had experienced an outside information process. So meaning that in a moment the star formation of Sagittarius was quenched, probably by the interaction with the Milky Way, but later star formation episode might have occurred, and while the gas had time to get enriched. Therefore, the later star formation episode brought to the formation of the metal-rich populations, while the metal-poor stars were dispersed and along the footprint. And we were able also to study and have a first insight on the old and metal-poor stellar population that is hosted in the galaxy. So this analysis had shown us how this dwarf system can be used as a workshop to test the combination of the Gaia data, and that has been combined by a photometric survey. And the power that comes from this combination enable us to investigate the history of this dwarf system. That is important also to gain a deeper knowledge on the Milky Way emerging history. And of course, there's still work to be done, because it would be very interesting to have high resolution spectroscopy for these stars, so to get elemental abundances and be able also to trace back the chemical history of Sagittarius. And we are excited also about the new data, the new Gaia data to test on our sample. And I thank you for listening.
Thank you very much for your presentation. Do we have any questions? Yes, please.
What criteria did you use to find -1.3 and -1 as the limits for the better reach and metal portion?
Yes. So there's not a we did not use a very strict criteria. We just tested with different metallicity cuts. So -1.3 was chosen for to be close to the value of the alpha need that's Sagittarius. So also to have an idea that stars, how were they distributed the stars before and after the occur of the knee. And -1 was chosen because it was for us a clear limit that for which we could fit the polynomials for the division. But actually, we test this analysis using, for example, -1.5 or -0.8, and we did find more or less always the same trend of the increasing of metal push stars moving along the footprint.
Thank you.
Great. Do we have any more questions? We have questions online. No. All right. So thank you for your presentation.